Welcome, deep divers. Today, we're taking a plunge into one of the most fundamental and, well, surprisingly contested areas of thought, the philosophy of science. We're going to unpack a core question. How does science really work? And, what makes it so distinctive?
Right.
Our source for this deep dive is an excellent introduction to the philosophy of science that tells a really compelling story of how the field has developed over the last 100 years or so.
And our mission, as always, is to pull out the absolute key insights for you, help you understand the debates, the arguments, and connect these evolving ideas about science to a broader understanding of knowledge itself. We really want to cut through all the noise, the information overload.
That's a core.
Exactly. Give you those essential aha moments. And as you'll see, we'll definitely move beyond the simple answers. We'll explore the complexities, the controversies, that have really shaped how we understand science's unique power.
Okay, let's dive in then. Our first challenge is surprisingly basic. It's defining what science even is. What activities truly count as scientific?
It seems simple, but it's not.
Right. On one hand, you have clear examples, like physics, heroic history, central role in understanding the universe.
Can't argue with physics, mostly.
Or molecular biology. I mean, its development has been so rapid, so impressive in recent decades.
Absolutely. But what's fascinating here is that even with these seemingly clear cases, you find hints of disagreement.
Really? Even there?
Yeah. Some argue that theoretical physics, for example, can drift too far into really abstract mathematical model building, almost disconnected, some say, from direct observation. And molecular biology, well, it's so intertwined with business and industry, its commercial aspects sometimes make people pause and question its pure scientific spirit.
Exactly. And this just points to a huge gray area, especially given the rhetorical power of the word science today. Calling something scientific, well, that often implies trust. Authority.
Oh, definitely.
While unscientific signals negativity, dismissal, so the very boundaries are kind of fuzzy, constantly debated. This also leads to different views on its historical scope. Some argue for a really broad view. They see science as, like, any systematic work assessing ideas through observational evidence, something found in all cultures throughout history.
A kind of general human activity.
Yeah. But others take a much narrower view. They see modern science as a very specific cultural phenomenon, localized in space and time, really emerging only from the scientific revolution in Europe.
And why does this distinction matter for you, the listener?
Well, ultimately, we need to grasp both things. How humans generally acquire knowledge, sure, but also what makes the modern scientific approach, the one forged in that scientific revolution, so uniquely powerful.
Right.
Most of the philosophical questions we'll tackle are broadly epistemological. That means they're about knowledge, belief, justification, that sort of thing.
But we'll also touch on metaphysical issues, questions about the fundamental nature of reality itself. And even some philosophy of language stuff comes into play.
And it's crucial, you mentioned this distinction before, between descriptive and normative theories.
Yes, very important. A descriptive theory aims to explain what actually goes on, what science is like. No value judgments.
Just describing.
Right. A normative theory, though, tells us what should go on. It sets out ideals, rules, how science ought to be done. And most views we'll discuss, even when they seem just descriptive, they often carry an underlying normative element.
Like a hidden should.
Pretty much. Then there's that incredibly slippery term, objectivity.
Yeah.
Sometimes it just means, the absence of bias. Fair assessment.
Makes sense.
Other times it refers to something existing independently of human minds, like objective reality. When we ask if science can describe an objective reality, we're wading into those deeper philosophical waters.
Okay. So, with these foundational questions buzzing around, what does this all mean for understanding how science actually works? Our source highlights 3 recurring fundamental ideas about what makes science tick.
Right. 3 big themes.
And you can see them as competing philosophies, maybe, or perhaps essential pieces of a larger, more complex puzzle.
Could be both.
The first one is empiricism, the idea that, quote, the only source of real knowledge about the world is experience. Now, you might think, well, duh, that's obvious.
Seems like common sense.
But historically, this wasn't always a trivial platitude, and even today, its implications are pretty profound.
That's absolutely right. Take the often tragic example of Ignaz Semmelweis, mid-19th century Vienna. Through careful observation, simple tests, he showed that doctors washing their hands drastically reduced deadly childbed fever in new mothers. a huge discovery based on experience. But he faced massive opposition. His empirical evidence wasn't enough to overcome established authority and, well, entrenched beliefs. It wasn't just about observation. It was about heeding the observation.
That's a powerful point. Okay, so experience is key, but maybe not always listened to. What about a success story?
Ah, yes. John Snow's work during the 1854 London cholera epidemic. Classic example of empiricism in action.
The Broad Street pump.
Exactly. He hypothesized cholera was spread by contaminated drinking water, meticulously mapped the outbreak, traced it to that specific public pump on Broad Street.
Against skepticism, right?
Oh, yeah, considerable skepticism. But he persuaded authorities to remove the pump's handle. And boom, the outbreak immediately stopped. It's a classic, really attractive case for simple, direct empiricism leading to clear, life-saving results.
Okay, so empiricism can work wonders.
It can. But then we have a crucial cautionary tale. Years after Snow's success, a brave German doctor, Max von Pettenkofer, he was convinced cholera wasn't solely waterborne.
Okay. What did he do?
He deliberately drank a vial of cholera-laced water to prove his point.
What? Did he survive?
He did, amazingly. But his experiment was deeply flawed. He failed to consider other factors that might have protected him, like maybe prior immunity or the specific bacterial strain wasn't virulent. Who knows?
So the observation him surviving didn't actually prove his point.
Precisely. It's not just a weird historical footnote. It's a stark reminder. Even well-intentioned empirical tests can go wildly wrong if the underlying theory or the experimental design is flawed. Data alone isn't enough. You need the right framework to interpret it.
That makes sense. Observation needs interpretation.
Okay.
What's the second big idea?
The second idea is the indispensable role of mathematics in science.
Ah, the numbers.
Right. As Galileo famously put it, the book of the universe is written in the language of mathematics. This idea suggests science's success is deeply tied to using mathematical tools to describe, to predict phenomena.
And this sometimes opposed pure empiricism.
Well, historically, sometimes it seemed that way. Galileo himself praised Copernicus for making reason conquer sense and believing the Earth orbits the sun, even when direct observation seemed to say otherwise.
So reason over eyes.
In that case, yes. But it's probably more accurate to see mathematics as an incredibly powerful tool within an overall empiricist outlook.
Okay.
I mean, Galileo, for all his rational arguments, was also a super keen empirical observer, using those improved telescopes, right?
Right, the moons of Jupiter and all that?
Exactly. But there's a crucial caveat here. Not all great science relies heavily on mathematics. Think about Darwin's On the Origin of Species.
True. Not much math in there.
Virtually none. Biology's really significant mathematical turn is actually a much more recent thing. It just highlights that different scientific fields can progress in different ways. Math isn't the only path.
Okay, good point. So we have empiricism with caveats, mathematics as a tool. What's the third idea?
And finally, the third idea is about the social structure of science.
How scientists work together or compete.
Both. This view suggests that science's unique organization, its communities, its mechanisms for cooperation, even its competition, is actually its most distinctive feature. Maybe the key to its success.
How so?
Well, historian Stephen Shapin argues against what he calls the mainstream empiricism's fantasy, this image of the lone scientist in a lab coat, testing everything all by themselves.
The isolated genius myth.
Exactly. Shapin emphasizes that science depends, crucially, on elaborate networks of cooperation and trust. Think back to John Snow. He relied heavily on others' testimony, data collected by others, to map that cholera outbreak.
He wasn't working in a vacuum.
Not at all. And the early scientific societies, like the Royal Society of London, founded way back in 1660. They were absolutely crucial here.
What did they do?
A key part of their role was efficiently allocating credit for discoveries, who found what first and fostering trust among members. This, in turn, encouraged the free spread of ideas. People were more willing to share if they knew they'd get credit and their peers could be trusted.
Ah, setting up the rules of the game.
Pretty much. The argument is that this specific social organization made scientific communities uniquely responsive to empirical experience, because ideas could be shared, debated, tested by a collective, not just one person.
So science isn't just brilliant individuals, it's a collective endeavor, built on trust, specific social rules.
That makes it uniquely responsive to what the world tells us. Yes.
So these three ideas, empiricism, math, social structure, they're all in the mix. And integrating the insights, especially from pure empiricism and the social side, seems like a key challenge for the philosophy of science.
Absolutely. It's a tension that runs through a lot of the debates we'll look at.
Okay. Now, to understand why these ideas became so fundamental, maybe a quick historical detour. You mentioned the scientific revolution.
Yeah, it helps to quickly sketch that period, mainly 16th and 17th century Europe, because the events and figures from this time carry special weight in these discussions.
Okay, so before this revolution,
You'd had figures like Aristotle dominating. His physics distinguish natural motion like a rock falling toward the center of the universe, its natural place from violent or unnatural motion like throwing the rock.
right, and the heavens were different.
Totally different. Heavenly bodies were made of an incorruptible fifth element, the quintessence, whose natural motion was perfect circles. Earthly stuff was corruptible, moved in straight lines.
Then came Copernicus, 1543.
Right, and Nicholas Copernicus proposed the Earth orbits the sun, a massive shift. But interestingly, his theory still relied on complex circular motions, epicycles, similar to the old Ptolemaic systems.
They're not instantly simpler.
Not really simpler in calculation, but it offered much better explanations for things like retrograde motion, why planets sometimes appear to stop and backtrack in the sky.
Okay. And then Galileo, early 17th century.
Yes, Galileo Galilei. He passionately championed the literal truth of Copernicanism. He used improved telescopes to make groundbreaking observations. Mountains on the moon, Jupiter's moons, phases of Venus.
Stuff that didn't fit the old model.
Exactly. And he developed a whole new science of motion. This, of course, famously led to his conflict with the Pope and eventual house arrest, a real clash.
And Kepler was around then, too.
Johannes Kepler, yes, also early 17th century. And he made the next crucial leap. He finally moved away from circles to elliptical orbits for the planets.
That was the key.
It led to a massive simplification of the system and greatly improved predictive accuracy in astronomy. It just works so much better.
Wow. Okay. And Boyle.
Robert Boyle, mid-17th century England. He really pushed for mechanism, the idea that phenomena can be explained by matter in motion, mechanical forces, but he embedded it in an organized research program. He urged systematic experiment, avoiding unempirical speculation. His approach was very influential in the founding of scientific societies like the Royal Society of London.
Bringing in that social organization aspect again.
Precisely. And this whole period really culminates with Isaac Newton, his Principia Mathematica, 1687.
The big one.
The really big one. It provided a unified mathematical treatment of motion, both on Earth and in the heavens. Newton showed how Kepler's elliptical orbits resulted from a universal force, gravity. He unified celestial and terrestrial physics.
Mind-blowing at the time, I imagine.
Completely transformative. His work seemed to complete large parts of physics for hundreds of years. This mechanical worldview became dominant, although, interestingly, it's kind of post-mechanical in some ways because forces like gravity weren't easily explained mechanically. They just were, hinting at mysteries still to come.
So this revolution sets the stage. It creates this powerful image of what science is and how it should operate.
Exactly. Which leads philosophers in the 20th century to try and really codify its essence, figure out the logic behind its success.
And that brings us neatly to the 20th century and the rise and, well, the eventual fall of logical positivism and its later more moderate cousin, logical empiricism.
Right. These were truly revolutionary philosophies in their day, born from this ambition to make philosophy as rigorous, as clear as science itself. Get rid of the fuzziness.
Okay, so what were their core ideas? Logical positivism first?
Well, it was heavily influenced by Einstein's relativity, but also huge developments in modern logic, mathematics, and the philosophy of language, especially early Wittgenstein.
A potent mix.
Very. A central idea was the analytic-synthetic distinction. They claimed analytic truths, like all bachelors are unmarried, are true just by definition. They're essentially empty of factual content about the world.
Okay, tautologies.
Right. In contrast, synthetic truths are factual claims about the world. They describe how things are, and they need observation experience to be confirmed. And crucially, they claimed all of mathematics and logic fell into the analytic category. Just reflections of how we use symbols, not descriptions of reality.
That's a big claim about math.
Huge. And then there was their philosophical weapon, as you called it. The verifiability principle.
Right, the meaning test.
Exactly. They initially argued that for any factual sentence to be genuinely meaningful, it had to be translatable into or verifiable by sentences that referred only to direct sensations, direct observations.
So if you can't test it through the senses, it's meaningless.
Pretty much, or at least factually meaningless. They used this principle really aggressively. to dismiss huge swaths of traditional philosophy, ethics, theology, arguing their statements couldn't be verified by observation, so they were just noise or expressions of emotion.
Wow. Okay, so what was philosophy's job then?
Very limited. Primarily logical analyses of how language, mathematics, and science work, clarifying concepts. They largely dismissed history and psychology as irrelevant to the philosophy of science that was just about how people happen to think, not about the logic of justification.
A very strict-down view of science, then.
Extremely. The resulting picture of science, and really all rational thought, was that its aim was simply to track and anticipate patterns in experience. Prediction was the name of the game. As one of them, Moritz Schlick famously put it, in science there are no depths. There is surface everywhere. No hidden reality, just observable patterns.
That sounds almost too simple. Did it hold up?
Well, no. Problems began to emerge pretty quickly, leading to logical positivism decline and its evolution into the more moderate logical empiricism.
What kinds of problems? Internal ones?
Yeah, partly internal struggles. It proved incredibly difficult to actually formulate the verifiability principle precisely. Every time they tried to patch a hole, like making sure scientific laws weren't rendered meaningless, they often created new problems or made the principle too weak to do its job of kicking out metaphysics.
A leaky ship.
Kind of. And then came major external attacks.
Like from Quine?
Exactly. The philosopher W.V.O. Quine delivered a massive blow in his paper, Two Dogmas of Empiricism. He powerfully attacked the core analytic-synthetic distinction itself.
He argued it doesn't really exist?
Essentially, yes. For Quine, all our ideas, our beliefs, form this interconnected web of belief. It only touches experience at the edges as a whole system. This meant, crucially, that no single statement, not even logical truths, could be considered absolutely certain or totally immune to revision in the face of surprising observations.
Wow, so even logic could be revised.
In principle, yes. Quine pointed to quantum physics as a case where scientists are contemplating revising classical logic to make sense of experimental results. This holism, the idea that beliefs face the tribunal of experience as a corporate body, not individually, was a profound shift. It meant knowledge isn't just stacking bricks, it's like maintaining a complex web.
Okay, so that really undermines the positivist project.
Big time. So logical empiricism, which emerged more prominently after World War II, became less aggressive, less revolutionary. They ditched the strict verifiability principle for something more holistic.
How did they deal with theoretical terms like electron? You can't see an electron.
Right. They argued that theoretical terms like electron gain their meaning not from direct translation into sensations, but from their place in a whole theoretical structure, a whole network, which, as a whole, connects to observable phenomena.
So meaning comes from the role it plays in the theory.
Exactly. But there was still this persistent empiricist aversion to hidden structures. The underlying idea remained that scientific language ultimately describes patterns in the observable realm. Prediction was still the primary goal, not necessarily describing some real hidden structure beyond what we could, in principle, perceive.
Still focused on the surface, in a way.
Still quite focused on the surface, yes. Which brings us, inevitably, to what's often called the mother of all problems in the philosophy of science.
Which is?
How observations actually confirm a scientific theory. How does evidence support a hypothesis?
Right. Not proof, but support.
Exactly. It's not about absolute proofs, which is rare in science, but about how evidence provides good reasons to increase our confidence in a theory. Think about induction, moving from particular observations to generalizations.
Like seeing lots of white swans leads us to say, all swans are white.
That's the classic simple example. But formalizing this for complex scientific theories involving unobservable entities and statistical claims turns out to be incredibly difficult.
Is this where probability comes in, like Bayesianism?
Yes. Using probability theory, particularly Bayesianism, has been a really promising approach. It offers a mathematical framework for understanding confirmation.
How does that work, roughly?
Well, the idea is that evidence makes a hypothesis more probable. For instance, discovering those unusually high levels of iridium in the Earth's crust, right at the dinosaur extinction boundary, that made the Alvarez hypothesis that a giant meteor impact caused the extinction much more probable than it was before. Bayesianism gives us tools to quantify that change in probability.
So it formalizes how we update our beliefs based on evidence?
Exactly. It formalizes updating our confidence. But this whole area is absolutely rife with incredibly tricky, mind-bending puzzles.
Ah, the fun part.
Oh yeah, deep philosophical weeds ahead.
Okay, hit me with one.
All right, first, the ravens problem, famously posed by Karl Popper.
Ravens all like blackbirds.
The hypothesis is simple. All ravens are black.
Mm-hmm.
Now, logically, this statement is equivalent to another statement. All non-black things are non-ravens.
Okay. If it's not black, it's not a raven. Makes sense. Logically equivalent.
Right. So here's the puzzle. If these statements are logically equivalent, then any observation that confirms one should also confirm the other.
Seems reasonable.
So consider observing a white shoe.
A white shoe. Right.
A white shoe is a non-black thing, and it's also a non-raven.
Right. Yeah, a white shoe is definitely not black and definitely not a raven.
So observing this white shoe confirms the statement, all non-black things are non-ravens.
Okay, following the logic.
But since that's logically equivalent to all ravens are black, observing a white shoe should, therefore, confirm the hypothesis that all ravens are black.
Wait, what? Observing my shoe confirms a hypothesis about ravens. That seems absurd.
Exactly. It feels completely wrong. This posed a huge challenge. Does confirmation depend only on the logical form of the hypothesis and the evidence statement? Or does the context of how we get the evidence matter? Like, was it part of a genuine test that could potentially have disconfirmed the hypothesis, like finding a non-black raven? Hempel initially leaned towards the purely logical view, which led to this paradox.
Wow. Okay, that definitely messes with your intuition about evidence. What's the other puzzle?
This one's even weirder, maybe. Goodman's new riddle of induction, involving the notorious invented word, GRU.
GRU. Okay, what's GRU?
Nelson Goodman defined it like this. An object is GRU if it was first observed before some future time, t, let's use 2010 AD as in the source, and is green, or if it was not first observed before 2010 AD and is blue.
Whoa, okay, so green if seen before 2010, blue if seen after 2010 for the first time. That's contrived.
Highly contrived, but logically possible. Now consider emeralds. Let's say up to today. Before 2010 in the example's timeline, every emerald we've ever observed has been green.
Standard observation supports all emeralds are green.
Right. That observation strongly supports the hypothesis all emeralds are green. But now consider GRU. Every emerald observed before 2010 has also been GRU because they were observed before 2010 and were green.
Okay, yeah. Fits the definition.
So, by the exact same inductive logic, observing many instances the observation all observed emeralds have been GRU should support the hypothesis all emeralds are GRU.
Following the pattern, yes.
But if all emeralds are GRU is true, what does that predict about emeralds we find after 2010?
According to the definition, if they're first observed after 2010, they would be blue.
Exactly. The hypothesis all emeralds are GRU predicts that emeralds first observed after 2010 will be blue, which is completely counterintuitive. We expect them to still be green.
So the same evidence seems to support two totally contradictory predictions about the future.
Precisely the paradox. The inductive arguments have the exact same logical form, but one seems perfectly good, all emeralds are green, and the other seems terrible, all emeralds are GRU.
So what's the takeaway? Logic isn't enough.
That's the profound conclusion. Confirmation, or good induction, cannot be a matter of purely formal logic. Something else must be involved.
Like what? You just rule out GRU because it's weird?
That's the obvious response. Say GRU is an artificial, inappropriate kind of predicate for induction, unlike green. Maybe green refers to a natural kind, and GRU doesn't.
Okay, that sounds plausible.
But Goodman had a clever counter. He argued that whether a term seems natural or contains a reference to time might just be relative to the language we happen to use. He invented another predicate, bleen, blue before 2010, green after, and showed how you could define our familiar green and blue using the seemingly artificial GRU and bleen.
Making green look artificial from a GRU-bleen perspective.
Exactly. His point was that trying to solve this by appealing to the naturalness of predicates like green might just push the problem back or reveal our linguistic biases. Maybe simplicity is the answer. But Goodman argued simplicity is also language relative.
Wow, so these problems are deep and persistent. They show that figuring out the logic of evidence is way harder than it looks.
Absolutely. They shook the foundations of logical empiricism and showed that a purely formal account of science was likely doomed. We need something more.
Okay, let's pivot then, away from the pure logic, perhaps, towards someone who brought in history and, well, sociology in a big way, Thomas Kuhn.
Ah, Kuhn. Yes, his 1962 book, The Structure of Scientific Revolutions, was just massively influential. Terms like paradigm and paradigm shift escaped academia and entered popular culture. He fundamentally challenged that neat linear picture of science, just steadily accumulating truths.
So what was his core idea? What's a paradigm?
A paradigm for Kuhn is more than just a theory. It's a whole way of doing science in a particular field at a particular time. It includes shared assumptions, key theories, standard experimental methods, even classic problems, and their accepted solutions, what he called exemplars. It defines the rules of the game for a scientific community.
Okay, like the accepted way of thinking and working.
Exactly. And most scientific work, what Kuhn called normal science, takes place within a paradigm. Scientists aren't constantly questioning the fundamental assumptions of their paradigm during periods of normal science. Instead, they're focused on puzzle solving, extending the paradigm's reach, making it more precise, applying it to new areas, ironing out minor inconsistencies. Good scientists in this phase are deeply committed to the paradigm.
So it's like filling in the details of a map, not drawing a new map.
That's a great analogy. But inevitably, anomalies start to crop up. These are observations or experimental results that just don't fit the paradigm, puzzles that resist solution.
Things that don't make sense within the current map.
Right, and when enough significant anomalies accumulate and scientists start to lose faith in the paradigm's ability to solve these problems, it can lead to a crisis. Confidence wavers. People start looking for alternatives.
And this is where revolutions happen.
Precisely. Scientific revolutions, for Kuhn, are these periods of considerable upset, non-cumulative episodes where an old paradigm is overthrown and replaced by a new, incompatible one.
Incompatible. How so?
This was one of Kuhn's most radical and controversial ideas. Incommensurability. He argued that paradigms separated by a revolution can be incommensurable, meaning they are hard, maybe even impossible, to compare directly using a neutral standard.
Why?
Because, he claimed, the standards of evaluation, the very concepts used, the problems considered important, even the way scientists perceive the world, can change with the paradigm. It's like the proponents of different paradigms are speaking slightly different languages or living in different worlds.
Living in different worlds. That sounds extreme.
It does. Think of the debate between, say, the biometricians and the Mendelians in early 20th century biology. They had fundamentally different ideas about what a good theory of inheritance should even look like, what kind of evidence counted, making direct comparison incredibly difficult. They were almost talking past each other.
Okay, I can see that. But different worlds. Literal or metaphor?
That's the big debate. Kuhn's most radical claim, often called the Chapter X claim, suggested that after a revolution, scientists literally work in a different world. Whether he meant this absolutely literally or more metaphorically was, and still is, heavily debated. He sometimes argued it was just more economical to think of it that way, given how perception itself could be shaped by the paradigm. It raised profound questions about scientific progress and objectivity. If standards change, how can we say science gets closer to the truth?
Yeah, that's the worry. So what was Kuhn's main contribution, despite the controversy?
His enduring contribution, I think, is showing that the success of science might lie in this delicate balance. A balance between the ordered cooperation and puzzle solving of normal science, which allows for deep investigation within a framework, and the disruptive, potentially chaotic, but ultimately reconstituting power of revolutions, which allow for fundamental breakthroughs.
So you need both order and disruption.
Exactly. Too much revolution and knowledge doesn't accumulate. Too much adherence to normal science and fundamental problems might never get solved. He compared it, and others like Stephen Jay Gould later picked up on this, to punctuated equilibrium in biological evolution. Long periods of stability punctuated by rapid bursts of change. It suggests a common pattern in how complex systems evolve, including science.
Fascinating. So Kuhn really stirred the pot, suggesting science is maybe messier, more human, less purely logical than the positivists thought.
Absolutely. And of course, other philosophers reacted strongly. Some tried to salvage rationality from Kuhn's picture. Others pushed the anarchic elements even further.
Right. You mentioned Lakatos, Lauda, and Feyerabend. How did they respond?
Well, Imre Lakatos was quite dismayed by what he saw as Kuhn's irrationalism, the mob psychology of paradigm shifts. He tried to offer a more rational account with this concept of a research program.
Okay, that's a research program.
Think of it as a sequence of developing theories, all sharing a common hardcore of fundamental ideas that adherents agree not to question, protected by a protective belt of auxiliary hypotheses that can be modified. Unlike Kuhn's single dominant paradigm, Lakatos argued that multiple research programs could coexist and compete within a field.
So competition is key for rationality.
For Lakatos, yes. This competition between programs, seeing which ones are progressive, predicting novel facts, versus degenerating, just patching up problems, was essential for rational choice between them. He distinguished change within a program, adjusting the belt, from the bigger decision of switching between programs.
And Loudon, similar idea.
Larry Loudon's research traditions were somewhat similar to Lakatos's programs, but maybe broader and more flexible. He included things like shared values and methods as part of the tradition, and he saw the boundary between the core ideas and the changing details as less fixed than Lakatos's hardcore.
Okay, trying to refine the picture of scientific change. But then there was Feyerabend.
Ugh. All Feyerabend, the self-proclaimed epistemological anarchist. His famous slogan was, "Anything goes."
Anything goes, seriously.
Well, he was being provocative, but he had a serious point. He saw science fundamentally as an expression of human creativity, like art. He advocated for a radical pluralism of ideas and methods. Let 1,000 flowers bloom, even if some are weeds, or even the ramblings of madmen, as he put it.
Why? Wouldn't that lead to chaos?
He argued, inspired by John Stuart Mill's defense of free speech in The Marketplace of Ideas, that true progress often comes from challenging established views, even seemingly crazy challenges. He believed established facts are often laden with hidden prejudices, and sometimes we need external, even irrational perspective to break free from the limitations of our current thinking. Sticking too rigidly to one method or one set of rules, he thought, could stifle the very creativity needed for major breakthroughs.
So a radical defense of intellectual freedom in science.
Extremely radical. So this whole debate after Kuhn boils down in many ways to this question: are there one process or two process theories of scientific change?
Meaning?
Is scientific change fundamentally one kind of process, like Popper's single model of conjecture and refutation that applies to everything from small adjustments to huge revolutions? Or are there two qualitatively different kinds of change, as Kuhn, Carnap, Lakatos, and Loudon all suggested in different ways change within a framework, normal science, tweaking the belt, versus change between frameworks, revolutions, switching programs?
Where does the current thinking lean?
It's still debated, but one interesting, more nuanced view comes from Peter Gallison. He studies the history of physics experiments and instruments. He argues that different elements of science, say, overarching theory, experimental practices, and instrument design often change at different times. They're not perfectly synchronized.
Like layers shifting independently.
Exactly. He calls the points where these different evolving traditions meet seams. And he argues these seams, this lack of perfect alignment, actually makes the whole structure stronger and more robust over time. It's not a monolithic block that shatters all at once, but a complex, layered structure that can adapt and evolve more flexibly, precisely because its parts aren't forced to change in lockstep.
That's a really interesting image. Science is this evolving, layered thing, not just paradigm shifts.
Yeah, it moves beyond the simple one process versus two process debate into something more complex and arguably more realistic.
Okay, so the internal debates within philosophy of science are clearly deep and ongoing. But what happens when the challenges come from outside its traditional philosophical boundaries? Let's turn to sociology. It feels like the focus shifts here, right?
It definitely shifts the lens. Science, once often viewed almost as this idealized, isolated pursuit of objective truth, starts being examined as a thoroughly human social activity.
And that starts with Robert Merton, the old sociology of science.
Right. Robert Merton is really the founder here. He viewed science primarily as a social enterprise, a specific kind of community with its own rules and values. He famously identified Merton's norms. These are the ideals that supposedly govern scientific behavior.
What are they again?
Universalism. Scientific claims should be judged on their merit, regardless of who makes them. Communism, or communality, the idea that scientific knowledge is common property. Disinterestedness. Scientists should act for the benefit of science, not personal gain. And organized skepticism. All claims should be subjected to rigorous scrutiny before acceptance.
Ideals, anyway.
Definitely ideals. Merton was well aware they weren't always followed. He also analyzed science's unique reward system. What motivates scientists? Primarily, he argued, it's recognition, especially credit for being the first to discover something. Think Boyle's Law, Darwinism, Halley's Comet. Scientists fundamentally desire to have their work used and acknowledged by their peers. That's the currency.
Okay, so that's the old sociology, focusing on norms and rewards. What changed?
Well, in the 1970s, a more radical approach emerged, particularly from the Edinburgh School, often called the Strong Program in the Sociology of Scientific Knowledge, SSK.
Strong program. What was their goal?
Their ambition was much broader: to explain why scientists come to believe what they do, why certain theories become accepted using purely sociological methods, not just describing norms, but explaining belief itself.
How?
Their key methodological principle was the symmetry principle. This was radical. It stated that when explaining scientific belief, sociologists should use the same kinds of causal factors to explain beliefs that we now consider true and beliefs we now consider false, or beliefs we deem rational and those we deem irrational.
Whoa, so don't assume truth explains acceptance.
Exactly. Don't just say, scientists believed X because X is true. Instead, look for social factors, interests, negotiations, local circumstances that led them to accept X, regardless of its ultimate truth value. They argued scientists weren't pure, disinterested thinkers operating solely on logic and evidence. Their beliefs were profoundly shaped by social interactions, power dynamics, professional interests, and local norms.
That sounds like it leads towards relativism.
It often did. Many proponents argued there's no single overarching external set of standards for rationality or evidence that applies universally. Instead, what counts as a good reason or sufficient evidence depends on the local norms of a particular scientific community at a particular time.
So saying science is the best way of learning is just our local norm.
From a strong relativist perspective, yes. It's just an expression of our cultural values, not necessarily a universally demonstrable truth. This, predictably, led to the tricky problem of reflexivity. If all knowledge claims are relative to social context, what about the claims of the strong program sociologists themselves? Are their claims just relative to their social context? This often led to tangled, sometimes interminable philosophical discussions.
I can imagine. Okay, who else was influential in this area? You mentioned Chapin and Schaeffer.
Yes. Stephen Chapin and Simon Schaeffer's book Leviathan and the Air Pump became hugely influential. It's a detailed historical study of the controversy between Robert Boyle, champion of the air pump and experimentalism, and Thomas Hobbes, who was skeptical of experiments and favored deductive reasoning in 17th century England.
What was their main argument?
They argued that Boyle didn't just discover facts using his air pump. He essentially created a new way of producing and validating knowledge. This involved not just the technology, the pump, but also new ways of organizing scientific work, witnessing experiments, public demonstration, new literary technologies, detailed experimental reports, and even new ways of talking about nature. They showed how Boyle subtly reconstrued tricky philosophical questions, like the existence of a vacuum, into problems that could be addressed by his experimental methods and managed within his specific social network for generating consensus. It was about building a trustworthy system for making facts.
So the social structure was inseparable from the knowledge produced.
Absolutely. And then you have Bruno Latour, another key figure, often associated with actor network theory. His early work, like Laboratory Life, co-authored with Steve Woolgar, was an ethnographic study, like an anthropologist visiting a strange tribe, but the tribe was scientists in a lab.
What did he find?
Latour claimed that scientific assertions start as tentative claims and are then processed, debated, modified, linked to instruments, inscriptions, allies, until they become stabilized and accepted as facts. The crucial controversial part was his claim that the intense human work involved in this stabilization process is then black-boxed or hidden, making the fact appear as if it were always just out there, independent of the work that made it.
So facts are constructed.
Latour famously stated that facts are created or constructed by scientific work. His work often deliberately blurred the line between describing how people decide what is real and making claims about what is real itself. He was very resistant to separating the social process from the knowledge outcome.
Okay, so this whole science studies approach, broadly speaking, seems pretty critical of traditional views.
Generally, yes. There is often a hostility to explaining scientific change primarily by appealing to a theory's better fit with the natural world. They were often suspicious of explaining a theory's popularity simply by saying it was more accurate or true. The focus was overwhelmingly on social, political, and rhetorical factors.
But doesn't that leave a gap? How does science connect so effectively to the world if it's all just social construction?
That's exactly the criticism often leveled against the more extreme versions. It sometimes seemed to leave little room for the idea that the natural world itself plays a significant role in constraining or guiding scientific belief. Which raises that fundamental question. If science is so deeply shaped by these human factors, what about its epistemic authority, its claim to give us genuine knowledge?
Right. And this question was amplified even further by another set of challenges coming from feminist critiques of science.
Indeed. The late 20th century saw a really significant shift here. Science's traditional image, as this purely objective, politically neutral, even anti-authoritarian force came under intense scrutiny. Feminist critiques argued that science, both historically and currently, often implicitly or explicitly perpetuates gender inequalities.
How so?
In multiple ways. By marginalizing women as participants and thinkers within science, by using biased methods or asking biased questions that ignored or distorted women's experiences, and sometimes by producing theories that reinforced harmful gender stereotypes.
Can you give an example, like the Lloyd book?
Yes. Genevieve Lloyd's The Man of Reason is a classic historical analysis. She traces how, in the Western philosophical tradition, the very concept of reason became strongly associated with maleness, while femininity was defined by traits seen as contrasting with reason, things like emotion, intuition, receptivity, connection to nature.
So reason itself got gendered.
Exactly. And she highlights figures like Francis Bacon, a key figure in the scientific revolution, using these pervasive metaphors of nature as female, something to be conquered, unveiled, penetrated by the masculine scientific mind. Knowledge is power, Bacon said, and the scientist was like a firm husband on the nuptial couch with nature, extracting her secrets for the improvement of mankind.
Wow, those are powerful metaphors.
And Lloyd argued these weren't just quaint historical artifacts. These deeply embedded metaphors subtly shaped expectations about who could be a scientist, what scientific thought even looked like, and the very relationship between the knower and the known, often influencing the structure and priorities of scientific inquiry itself.
Okay, that's the historical critique. Are there more concrete examples of gender bias affecting actual scientific findings?
Absolutely. A really clear, tangible example comes from primatology.
Studies of primates, okay.
The older view, developed when the field was overwhelmingly male-dominated, often depicted female primates as relatively passive, mainly concerned with mothering, with social life, and mating, largely controlled by dominant competitive males.
The alpha male narrative.
Pretty much. But starting around the 1970s, as significantly more women entered the field, a very different picture began to emerge. Researchers like Sarah Blaffer-Hrdy, through careful, detailed observation, started documenting active, complex female sexual strategies, female competition, and sophisticated ways females manipulated males within primate social groups.
So the view of female primates changed dramatically.
Dramatically. And this profound shift in scientific understanding directly coincided with the changing demographics of the field. The strong suggestion is that the women entering primatology, perhaps bringing different perspectives, maybe different observational sensitivities, or simply being less bound by the old male-centric assumptions, were able to see and document behaviors that had previously been overlooked or misinterpreted. It suggests their identities and experiences influenced the scientific findings in a way that led to a more accurate picture.
That's a compelling case. So this leads to feminist epistemology, thinking about knowledge itself from a feminist perspective.
Exactly. Feminist epistemology critiques how science traditionally handles evidence, frames questions, and organizes its social structure, arguing these aspects are often subtly gendered.
Are there different approaches within feminist epistemology?
Oh yes, several. Some more radical approaches draw on postmodernism, embracing a kind of relativism. They might argue there's no single true description of the world, and that different descriptions might be valid for different genders or social groups, reflecting their different experiences.
Oh, okay. What else?
Another influential approach is standpoint epistemology. The core idea here is that one's situatedness, one's position in the social world, including gender, race, class, isn't just a source of bias, but can actually be an epistemic strength.
How can being marginalized be an advantage for knowledge?
The argument is that marginalized groups, precisely because they are outside the dominant power structures and perspectives, may be able to see things that are invisible or taken for granted by those in positions of power. They might have insights into social relations or even natural phenomena that are missed by the mainstream. Proponents often cite examples like Barbara McClintock, the biologist who discovered jumping genes. She described having a unique feeling for the organism, a more holistic, intuitive approach that differed from the prevailing reductionist methods of her male colleagues, and which ultimately led to her Nobel Prize-winning discovery.
So different perspectives can enrich science.
That's the core claim of many feminist epistemologists. Acknowledging who is doing the science and from what perspective isn't about abandoning objectivity, but potentially about achieving a more complete or less biased understanding by incorporating diverse viewpoints and experiences.
Okay, so we have these powerful challenges coming from sociology, from feminism, questioning the traditional image of science. Where does philosophy of science go from here? Is there a way to integrate these insights without completely giving up on rationality or objectivity?
That's the million-dollar question. And one major response within philosophy itself has been the rise of naturalistic philosophy or naturalized epistemology.
Naturalism. What's the core idea?
The core idea, often associated with Krein initially, is that philosophy should be continuous with science. It rejects a sharp separation between philosophical questions about knowledge and scientific findings about how humans actually think, learn, and interact socially.
So use science to study science. Isn't that circular?
It sounds potentially circular, but naturalists argue it's not a vicious circularity. It's more like using our best available tools, which include scientific findings about cognition, psychology, sociology, to understand how knowledge, including scientific knowledge itself, is acquired and justified. It's seen as a necessary resource, not a forbidden move.
Okay. Does naturalism just describe how science happens, or can it still address those should questions, the normative ones?
That's a key point. Many naturalists believe philosophy still has a crucial normative role. It still addresses questions about how we should reason, how we ought to handle evidence, what makes for good justification. But it does so informed by our best scientific understanding of how beliefs are actually formed and how scientific communities do function. Science provides the descriptive input. Philosophy refines the normative goals in light of that input.
Okay, so how does this naturalistic approach apply to understanding, say, the social structure of science that Merton and the Strong Program folks were looking at?
It provides a different lens. Take David Hull's work, especially his book Science as a Process. He offered a thoroughly naturalistic account of science, drawing on evolutionary biology and sociology. He argued, like Merton, that science thrives on this delicate balance of cooperation and competition.
Okay, but what drives it, according to Hull?
Hull proposed that scientists are primarily motivated by a deep-seated desire for recognition, but specifically the recognition that comes from having their work used by other scientists. Citations are key. Getting your ideas, your data, your methods incorporated into the work of others is the ultimate reward.
So it's about influence.
Exactly. And this desire for influence, for credit through use, paradoxically drives the free sharing of ideas. You had to publish your ideas, make them available for others to use them and cite you. This creates a system, Hull argued, where individual ambition, the desire for credit, actually serve the collective goal of advancing knowledge. It's almost like an evolutionary system selecting for useful, shareable ideas.
An invisible hand guiding science.
Very much like that. Hull even contrasted his view with Popper's emphasis on severe testing. Hull argued individual scientists don't necessarily need to be hypercritical of their own ideas. The competitive nature of the community ensures that others will provide the necessary criticism and checks. The system takes care of it to some extent.
That's interesting. Does this connect to the history, like the Royal Society?
Hull and Merton both noted how modern science developed particularly successfully in European societies that were already comfortable with certain forms of individual competition. And institutions like the Royal Society skillfully developed mechanisms, rapid publication, priority disputes, eventually peer review to manage this competition, allocate credit fairly, mostly, and encourage the sharing needed for collective progress.
So the social system matters, but maybe in a way that promotes reliable knowledge.
That's the naturalist argument. Philip Kitcher developed similar invisible hand models, showing mathematically how individual scientists making self-interested choices about which research programs to pursue could, under certain conditions, lead to an optimal distribution of effort for the community's overall success, even without central planning. Though others, like Michael Strevens, have critiqued these models, pointing out potential problems like free riding.
Okay, so naturalism tries to explain how the social dynamics can actually contribute to science's success. How does this connect back to the feminist critiques?
Well, the naturalistic focus on competition and reward systems also provides a framework for understanding some feminist concerns. If the culture becomes hyper-competitive, or defines success too narrowly based on who shouts loudest or publishes fastest, it might indeed exclude valuable alternative styles of thinking, or different ways of engaging with nature like McClintock's feeling for the organism. A system optimized for one kind of success might inadvertently filter out other valid approaches, potentially reducing the intellectual diversity that fuels long-term progress. So the balance is crucial.
That makes a lot of sense. Okay, this discussion of social structures, bias, and how science connects to the world inevitably leads us to the really big overarching question: scientific realism.
Ah, yes. The elephant in the room for much of philosophy of science. Does science actually describe a real world that exists independently of our minds? Or is it just a useful tool for predicting experiences?
How do we define scientific realism carefully?
It's important to be clear. Scientific realism isn't usually the naive claim that our current theories are perfectly true and complete. That would be foolish, given history. Rather, it's typically the view that a reasonable aim of science is to provide true, or approximately true, descriptions of reality, including the unobservable aspects of it. Things like electrons, genes, black holes. Science isn't just about saving the observable phenomena, it's trying to tell us what the world, hidden parts and all, is really like.
So, aiming for truth about the unobservable, what are the main arguments for and against it?
Well, the debates often swing between optimism and pessimism. The main argument against realism is often called the pessimistic induction from the history of science, or pessimistic meta-induction.
Meaning?
Look at the history of science. It's littered with theories that were once highly successful, empirically adequate, widely believed, but whose central theoretical entities, things like phlogiston, caloric fluid, the luminiferous ether we now believe don't exist at all.
Right. Theories that worked for a while but were fundamentally wrong.
Exactly. So the pessimist argues, if so many past successful theories turned out to be wrong about the unobservable entities they postulated, shouldn't we expect our current successful theories to suffer the same fate? Why should we believe in electrons or quarks if phlogiston and ether failed?
That's a strong argument. How do realists respond?
Optimistic realists counter with their own lists. Look at the incredible, long-term, detailed predictive and manipulative success we've had based on theories about atoms, molecules, germs, genes, electromagnetic fields. The entities postulated by these mature theories seem incredibly well confirmed and are woven into countless successful technologies. The no miracles argument suggests it would be a miracle if these theories worked so well unless they were capturing something real about the unobservable world.
So it's a battle of historical examples.
To some extent. But realists also try to refine their position. Maybe realism is only warranted for mature sciences or theories that have generated truly novel predictions that were confirmed, and it's crucial to recognize that confidence levels should vary. We might be much more confident about the reality of, say, atoms or the basic structure of DNA and molecular biology than about the ultimate nature of dark energy or the entities postulated by cutting-edge string theory in fundamental physics. Realism isn't an all-or-nothing game.
Okay. What are the other major challenges to scientific realism besides the pessimistic induction?
Well, there's the challenge from traditional empiricism, which we touched on earlier. If our only access to the world is through our senses, through experience, how can we ever really know or even meaningfully talk about things that are, by definition, unobservable? There's a worry that our language derived from experience might not genuinely reach or refer to things beyond that veil of ideas or sensations.
The limits of language and experience.
Exactly. Then there's a more radical challenge from various forms of metaphysical constructivism. This is the idea we saw hinted at in Kuhn, Latour, and even Goodman. It's the claim that the world science describes isn't simply out there waiting to be discovered, but is in some significant sense created or constructed by our theorizing, our language, our paradigms.
So reality itself depends on what we think or say. That sounds very counterintuitive.
It is. It's a very difficult position to interpret clearly and consistently, but it has been influential. It's often rooted in a deep opposition to the idea of a passive mind simply receiving or mirroring an independent reality. Constructivists emphasize the active role of human concepts and practices in shaping the world we experience and investigate.
Okay. And the third challenge, instrumentalism.
Right. Instrumentalism, most famously defended in modern times by Bas van Fraassen with his constructive empiricism. This isn't as radical as constructivism. Instrumentalists don't deny there is an independent reality, including unobservable parts, but they argue that the aim of science isn't, and shouldn't be, to achieve truth about that unobservable reality. Instead, science aims only for empirical adequacy.
Meaning it just has to get the observable predictions right?
Pretty much. A theory is empirically adequate if what it says about the observable parts of the world, past, present, and future, is true. Whether its claims about unobservable things like electrons are also true is irrelevant to the success of science, according to Van Fraassen. We should accept theories as empirically adequate, but remain agnostic about the reality of the unobservables they postulate. Belief in electrons is a leap of faith science doesn't require.
How do realists respond to that? Why aim for more than just predicting observations?
The realist often pushes back by asking, what is so special about the detectable? Why draw this arbitrary line between what we happen to be able to observe, which changes with technology anyway, and the rest of reality? If our theories give us good reason to believe in electrons, and those beliefs help us explain and predict observable phenomena, why arbitrarily withhold belief just because electrons are unobservable? Science, the realist argues, should aim to describe all aspects of the world it can reliably gain information about, observable or not, adjusting our confidence levels as appropriate based on the evidence. Stopping at the observable seems artificial.
Okay, that makes sense. This also seems to connect to how science uses models, not just language.
Absolutely. Much contemporary philosophy of science focuses on models as the primary representational vehicles of science, not just linguistic statements. Think of the billiard ball model of gases, the double helix model of DNA, climate models. These are often abstract mathematical structures or physical analogies or computer simulations.
And models aren't necessarily true or false in a simple way.
Exactly. They represent certain aspects of a target system, idealizing or ignoring others. They offer a lot of flexibility. We can talk about how well a model fits the data or how useful it is for certain purposes without necessarily having to claim the model is a literal, true description of reality in all respects. This focus on models allows for a more nuanced discussion than just debating whether a linguistic theory is true. Some philosophers even argue that truth itself isn't a particularly helpful concept for analyzing scientific practice. Maybe it's more of a social signal we use to endorse theories we find reliable.
Interesting. Okay, so realism is complex. Let's shift back to something maybe more intuitive. Explanation. Science doesn't just predict. We want it to tell us why things happen.
Yes, the desire for explanation seems fundamental. We want to know why the sky is blue, why diseases spread, how photosynthesis works. It's about understanding causal connections and mechanisms.
Well, empiricists were suspicious of this too.
Historically, yes. Some hardcore empiricists saw explanation as a kind of unnecessary extra goal beyond just accurate prediction and description of regularities. If you can predict perfectly, what more do you need?
What about the covering law theory? That seemed like an attempt to formalize explanation.
It was. Karl Hempel's covering law theory was hugely influential for a while. The basic idea was that to explain a particular event or phenomenon, you had to show it could be logically deduced from one or more general scientific laws, plus some specific initial conditions. Explanation was essentially a logical argument.
Why did it fail?
It ran into lots of problems. It couldn't handle statistical explanations well. It tried to count some things as explanations that clearly weren't, like explaining why a flagpole's shadow has a certain length by deducing it from the sun's angle and the flagpole's height that predicts, but doesn't really explain why the shadow is that long in the way citing the flagpole blocking light does.
Yeah.
And crucially, it didn't seem to capture the central role of causation in many scientific explanations. It missed the feeling of knowing why.
So what replaced it, if not laws, then what?
Two main approaches gain prominence. One is the causal theory of explanation. This emphasizes that explaining something often involves describing the underlying causal mechanisms how things work. Explaining photosynthesis means detailing the biochemical pathways, the role of chlorophyll, light energy, etc.
Makes sense. What's the other approach?
The unification theory of explanation, associated with philosophers like Michael Friedman and Philip Kitcher. This view argues that explanation consists in unifying a wide range of different phenomena under a smaller number of basic principles or patterns. Newton's laws were a great explanation because they unified celestial motion, terrestrial motion, tides, etc. under one framework. The more you can unify with fewer principles, the better the explanation.
Are these competitors? Causal versus unification?
Not necessarily. Many philosophers now think that good scientific explanation often involves both identifying causal mechanisms and showing how those mechanisms fit into broader, unifying patterns or laws. They might be complementary aspects of understanding. And crucially, different scientific fields might have different standards or emphasize different aspects of explanation. What counts as a satisfying explanation in particle physics might be different from ecology or sociology. It's a concept internal to science, but varied.
Okay. This talk of causes and laws brings up deep metaphysical questions again, doesn't it?
Oh, yes. What is causation, really? Is it some kind of real connection or force in the world, the cement of the universe, as J.L. Mackie called it? Or is the Humean view correct that causation and laws are ultimately just descriptions of regular patterns, constant conjunctions of events with no deeper governing necessity? These are huge ongoing debates in metaphysics that underpin how we think about explanation.
Right. Deep stuff. Okay, let's circle back to confirmation, the evidence problem. You mentioned Bayesianism as a promising approach earlier. Is there more hope there now, maybe combined with naturalism?
Yes, there's definitely renewed interest and, some argue, significant progress. particularly when Bayesianism is combined with a more procedural and naturalistic understanding of evidence.
Remind us quickly how Bayesianism works.
Okay, the core is Bayes' theorem. It's a mathematical rule for updating probabilities. You start with a prior probability, your initial degree of belief and a hypothesis before seeing new evidence, let's say pH. Then you get some evidence, E's. You need to know the likelihood. How probable is it that you would see this evidence if your hypothesis were true? That's pH. And also, how probable is the evidence if the hypothesis is false? pH. Bayes' theorem then tells you how to combine your prior belief with these likelihoods to calculate the posterior probability, your updated degree of belief in the hypothesis, after considering the evidence, pA.
The car at the party example.
Exactly. My prior belief my friend is at the party might be 50%, P 0.5. Seeing their car E is likely if they're there, say P 0.8, but unlikely if they're not, say P 0.1. Plugging these into Bayes' theorem gives me a much higher posterior probability, around 89% in this case, P 0.89. It formally captures how evidence changes belief. What are the main challenges for Bayesianism?
A big one has always been, where do the prior probabilities come from? If they're just subjective degrees of belief, doesn't that make confirmation subjective? Different people, starting with different priors, might reach different conclusions from the same evidence. Subjectivists argue that over time, with enough evidence, priors tend to wash out and people converge. Others try to find more objective ways to set priors. It's a complex debate.
Okay, but how does this help those weird puzzles like Goodman's GRU?
This is where combining Bayesianism with the procedural or naturalistic perspective seems really powerful. Consider GRU again. Green before 2010, blue after. From a procedural viewpoint, the very definition of GRU-ness makes the act of observation before 2010 part of the property itself. Observation becomes a factor in the definition.
Right. This means that observing emeralds before 2010 gives you information about a sample that is inherently biased with respect to the property GRU, because the observation date is part of the definition. You cannot logically extrapolate from all observed emeralds were GRU, meaning observed before 2010 in green, to all emeralds, including those observed later, will be GRU, meaning those observed later will be blue. The sampling procedure is fundamentally confounded by the definition of GRU.
So the problem isn't the logical form, it's that GRU messes up the sampling procedure needed for good induction.
Exactly. Unlike greenness, where observing an emerald doesn't conceptually depend on the date it was observed, this procedural naturalism dissolves the paradox by showing why the induction works for green but fails for GRU. It's not about arbitrary predicate choice. It's about whether the property allows for unbiased sampling and extrapolation. Procedures matter fundamentally.
That feels like a much more satisfying solution. Does this procedural view help elsewhere?
Yes, it helps clarify how scientists actually reason in many cases. Think about eliminative inference.
Ruling things out.
Right. Sherlock Holmes saying, when you have eliminated the impossible, whatever remains, however improbable, must be the truth. Scientists do this all the time. Darwin argued for natural selection, partly by eliminating alternative explanations like special creation. Galileo argued for his physics by showing problems with Aristotelian physics. You strengthen a hypothesis by ruling out its plausible competitors.
Makes sense. What's the catch?
The big challenge, of course, is knowing whether you've identified and considered all the relevant alternatives. Maybe the true explanation is one you haven't even thought of yet, but focusing on elimination helps us understand both successes, when the true hypothesis was among those considered, and failures, when it wasn't. And it again highlights the importance of procedures. How are the alternatives generated? How are they tested and eliminated?
And this procedural focus helps with the Ravens problem too, the white shoe.
Precisely. A randomly encountered white shoe tells you almost nothing about ravens because it wasn't generated by a procedure designed to test all ravens are black, like sampling ravens, or even its contrapositive, all non-black things are non-ravens, like sampling non-black things. A white shoe found during a systematic random sample of non-black things would provide some tiny confirmation, but one found incidentally provides virtually none. The procedure by which the evidence is obtained is crucial to its evidential weight.
Okay, so focusing on procedures informed by naturalism and maybe using Bayesian tools offers a much richer, more realistic picture of how scientific evidence works.
I think so. It moves beyond the purely formal problems that plagued earlier empiricism and gets closer to understanding science as a dynamic, procedural, and, yes, social activity.
So after this whole journey through definitions, history, paradigms, social critiques, realism debates, confirmation puzzles, where do we land? How should we think about science now?
Well, maybe we end up with a kind of reformed empiricism. Science isn't just about raw experience, but it is fundamentally about checking our ideas against the world through experience. It seems to be a dual entity. On one hand, a very general human strategy assessing ideas by systematically exposing them to experience, trying to learn from feedback.
Found everywhere to some extent.
Right. But on the other hand, modern science is also a very unique, socially organized, and constantly evolving way of carrying out that general strategy much more effectively. Its power seems to lie in its cumulative nature, its error-correcting mechanisms, and that efficient, if sometimes messy, blend of cooperation and competition, guided by specific procedures and norms.
And what about objectivity? Can science give us objective knowledge despite all the human elements?
That remains the core question. But perhaps the best answer is that science, when it's working well with its checks and balances, its critical culture, its responsiveness to evidence, even if filtered through paradigms and procedures, tends to produce beliefs that are progressively shaped and constrained by the way the world actually is. It's not perfect, it's fallible, it's influenced by society, but its procedures often give the real things in the world a powerful voice in guiding our beliefs about them. So maybe a qualified procedural objectivity is achievable.
So despite all the complexities and debates, we have made progress in understanding science.
I think so, definitely. We've moved beyond overly simplistic views, whether purely logical or purely social. We have more nuanced understanding of realism, a better appreciation for the role of models, and more sophisticated theories of evidence that incorporate probability and procedure. It's still a work in progress, but the philosophical picture is much richer now.
Okay, a final thought then for you, our listener, to take away. If science, as we've seen, is constantly negotiating these delicate balances between cooperation and competition, between sticking with established frameworks and embracing revolutionary ideas, between its own internal standards and external societal influences, what might that mean for how you should approach understanding complex information in your own life, in your work? Where might you be relying on a seemingly simple story or an obvious answer, when perhaps a more complex balance or a deeper look at the procedures involved is actually what's needed to truly understand? Something to ponder.